Okay, let's continue the class. Uh, I want to briefly tell you uh, about the future plan of our class. Actually, the modern robotics class usually had the project, uh, a project instead of final exam. But in this class, in this time, I prefer to take an exam, final exam. So actually, there is not much time to proceed the final project. So I think it is better to take an exam in the uh, fifth week, 15th week. So about the schedule, today is Monday, and this is fifth 12 week and 13, 14, and 15th week. So in this week, we will have final exam, and actually our class is a little bit delayed, so I'm sorry about that. But my goal is to complete the inverse kinematics and Jacobian will be finished in this week, and 12th week we will take dynamics. Actually, dynamics is one of the very important topic in this class. So I will finish dynamics through 12 to 13. So, and then we will take an exam in here. So actually, the class will be finished here, and 14th week will be problem solving or some kind of problem examination examples. I will show some problem solving example, and then you will take an exam 15th week. Similarly to the midterm exam, I will give you the solution. Actually, I already uploaded solution about chapter 4. So chapter 4 is about the forward kinematics. So you can solve some of the practice problem, and you can practice your own. And after we finish our Jacobian and inverse kinematics, I will also upload some solutions. So chapter 4 is about forward kinematics, and this is a important part. And in this week we will study about the velocity kinematics. I mean, there is the Jacobian, and then next week we will study about actually the inverse kinematics also deal with in this week. And chapter 7 will be ignored, skip. And then we will study about chapter 8 in the next week. So the final exam problem will be chapter 4, 5, chapter 8. So final exam will be chapter 4, 5, 8. So you may study about this chapter, but I will give you some hint about the final exam when in this class. So actually the final exam range is quite broad and wide, so it might be difficult. So I will give you some hint in this week, and from time to time. So in this week we will study about Jacobian. As I told already, Jacobian is about the velocity kinematics. Actually, the kinematics is about the position and orientation, but in sometimes we want to know about the velocity relationship between space frame, body frame, space frame and body frame. So these kind of things can be calculated by Jacobian. So if you already take the modern robotics class, undergraduate class, then you might know the concept of Jacobian, but concept of singularity and manipulability will also, you already know about this one. So in this class, I will briefly introduce, and we will focus on the Jacobian. So previously, we learned about the space form of POE. So in the space form POE, we only need to know the space screw and initial configuration. And this form can be transformed to the body form using this kind of calculation. So this M matrix moved from last position to the first position, and all the screw axis is changed from space form to body form. So in here, the important thing is this one. The screw axis in the space frame can be converted to the space screw axis on the body frame. So in here we used M matrix, M inverse M inverse here and M here. So actually this calculation is equal to the concept of outer joint. So about this, I already told you. We already learned about this in here. In the rigid body motion, we learned about in the chapter 5, class 5, we learned about the concept of twist. And when we learn about the twist, we already learned about this concept. T inverse, actually T is changed to the M. and this twist can be converted, space twist can be converted to body twist. So this concept was introduced as other joint. So same thing can be applied here, like this. Yeah, there it is. So from lecture 5, we already learned about the space twist, the 6-vector form, and this space twist can be converted as a small SE3 matrix form, and in this SE3 matrix form, if we multiply T inverse T, then it can convert space screw to body screw. And if we make the order joint matrix 6 by 6 order joint matrix, then if we multiply order joint matrix in front of 6-vector form twist, then we can get the 6-vector form body twist. So this calculation is SE3 form calculation, and this one is 6-vector form calculation. So there is two way of calculation using order joint. So it is very important to keep in mind about this one. And then let's continue to the velocity kinematics. So we know about this forward kinematics equation. From this one, we should derive the velocity kinematics. So the velocity is the derivative of the position. So this is position level. So we take the time derivative of this one. Then dt, d large capital T, dt equal t dot. This one is time derivative of homogeneous transformation matrix. So if we take the time derivative of t, then we can time derivative this one. This is multiplied. This equation is multiplying product of exponential coordinate production. So all these components should be time derivative like this. The first element is time derivative, and then plus, and then second element time derivative plus, and then third element time derivative. So if we write down here, we can write down like this. So this one, if we take the time derivative of this one, so using this equation, so if we take the time derivative of exponential a theta, then this part is take the time derivative, and a is constant, the theta becomes theta dot, and then this exponential part is just remained. So it becomes like that. So in here, the screw axis is remained, and then theta 1 becomes theta 1 dot, and then this part is remained, and all the other things is remained. So this equation is first part is time derivative, and this part is second element is time derivative. So this one becomes plus n times. And then if we multiply T inverse is like this, because if we take the inverse of this equation, then all the product order is reversed. So M came out first, and this one came out second, and this one is go to the last position. And we add inverse index here like that. So if we multiplying this equation, t dot t inverse becomes t dot t inverse become like that. In here, if we multiply this one and the first element, uh, this one is erased, and this one is erased, and all the other things is erased, and this one is only remained like this. And if we do these things in the second element, this one is erased, and this one is erased, and this one is erased, and then okay, and this part is erased, and this one and this part is remained, so it remained like this. And if we do these things with these other things, if we multiplying all the other things, then we can make general expression. In here, we already learned about t dot t inverse is equal to the space twist of SE3 form, small SE3 form. So in here, let us see about this one. If there is a T matrix, homogeneous transformation matrix, and this adjoint T convert space twist to the body twist, and the other format is something like this, and this is equal to this expression. So this one is six vector form expression, and this is small s3 form expression. And actually the result is same. So about this one, this expression can be converted like this. So this is the one of the homogeneous transformation matrix. So we put this one here, and we put S2 here. So this one is the same. This one has applied the same principle with this one. So if we simplifying this one, this equation, we can get the six vector form general equation of Jacobian. This one is six vector form space twist. So in here, we can find the Jacobian matrix. So this one is S1 Sierra 1 dot, and this one is multiplied with Sierra dot 2, and this one is multiplied with Sierra dot 3. When we make the Jacobian equation, Jacobian matrix, all the component multiplied with Sierra dot element becomes the column of the Jacobian. So this becomes the first column of Jacobian, and this becomes second column of Jacobian, and this becomes nth column of Jacobian matrix. So as a result, we can get the general expression of space Jacobian. In the Jacobian, there is two type of Jacobian. When we get the world kinematics, there was two type of POE. One is space POE and second is body POE. Similarly, in the Jacobian, we also have space Jacobian and there is body Jacobian. So in the space Jacobian, the general expression of Jacobian column vector becomes like this. Jacobian column vector is same with this equation. This equation. And let's think about the meaning of the Jacobian column matrix, column vector. Actually, this one is space screw axis, and this one is other joint. And if we multiplying other joint, it becomes some kind of other screw axis. So actually, this JSI is equal to the screw axis, some kind of screw axis, but a little bit transformed form. So actually, Jacobian column vector can be written like that: omega si vsi, the function of theta. So I will interpret this one. JSI is equal to the ice screw axis based on the fixed frame when the manipulator is rotated by theta. I will explain more detail. In our textbook, there is ice column of JSI is equal to this equation. And actually, this one is SI is transformed using this other joint matrix. So the meaning of JSI describe this one. Each column JSI theta is screw vector describing joint axis I expressed in the fixed coordinate but arbitrary theta rather than theta is equal to the 0. That means this one describing screw axis, but not about theta equal 0, but about some theta. So some theta variable. So I will explain more detail about this one using the example. Okay. Before then, we will remind this expression. We need to remind this expression. Actually, this one is twist. And this one is theta. And this one is Jacobian. Actually, in in the modern robotics class, the final goal, our class is to describe rotational movement and translational movement is expressed in the one format. So similarly, in this Jacobian, we also expressed the rotational movement and linear movement is expressed in the one format using twist. And using this Jacobian, we can convert this joint movement to the or the rotational movement with the linear movement. Let me break a little bit.